Okay, let's see where we are. Okay, so we've turned atoms into ions, stuck those ions together, and then rearranged them a couple of different ways in a few different reactions, and learned to keep track of where the atoms go by balancing each side. Let me just check that there's nothing extra for me to do. Okay, right, so what we'll do now is we'll talk about solutions, because most of the time when we mix two chemicals together and expect them to react, those chemicals will not be as solids. They could potentially be gases. You mix a couple of gases together, they could react. But gases are difficult to handle, so we don't do an awful lot of that. What we mostly do is take solids and dissolve them in something else, a solvent, and then have the chemicals react while they're in solution. So let's talk about this. This gets to be chapter 4. Chapter 4 is about solutions. All right, what was our definition of a solution? We've already seen solutions once. What was it that was special about solutions? The particles become so finely divided that we lose visible contact with them. Yeah, so this is a homogeneous mixture, and we lose track of the solute because it becomes so finely divided that we just can't see it anymore. So the solute dissolves in the solvent to become solution. Okay. And we had previously talked about that you can dissolve liquids in liquids, you can dissolve solids in liquids, you can also dissolve gases in liquids. It is possible to dissolve metals in metals. That makes alloys. Shouldn't think of that as being two solids dissolving in one another. That's not really the case. And gases, because the gases are already finely divided, we're not going to call two gases in the same space a solution. They're just mixtures, because the gases act completely independently of each other. Okay. Let's look at what we can have. We can have solids in liquids, we can have liquids in liquids, and we can have gases in liquids. Gases dissolve in liquids. Some, you've got to get it right. Solids dissolve in liquids. Some, you have to get it right. Not all solids are soluble. Some of them are insoluble. That's the whole theory behind, sedimentary rock. We talked a week or so ago about limestone. This area is full of limestone. At one point, all of that was in water. All of that at some point was dissolved, and then the calcium and the carbonate found each other and decided they're only a tiny bit soluble in water, and it falls to the bottom. So you can have things that will dissolve, which are going to be called soluble. And you're going to have things that will not dissolve, which are called insoluble. Now, for reasons that will not be explained, liquids that dissolve in other liquids are not called soluble. Use the word soluble. If you said that alcohol was soluble in water, everyone would understand what you meant and we'd be okay with it. But there is a special word. Miscible versus immiscible. And I think I'm spelling that right, but putting two M's up front. I think so. And then we go back to being soluble or insoluble. Gases in water. Okay. Let's put our middle school science question thinking caps on. And answer a very simple question. If I gave you a piece of solid and said, okay, as soon as you make that dissolve in water, you can go. That's your task, that's lab for this afternoon. If you can make the solid dissolve in the liquid, then your task is complete and you can go. What could you do to aid the dissolution process?
Heat.
Ooh.
Mix something up. Increasing its temperature.
I could heat the liquid up. If I gave two separate people 10 grams of salt and a 100 milliliter beaker filled with water, and this side of the room heated that water up, and this side of the room didn't, this side would be finished first. Because heat increases the solubility of solids. In liquids, well, most of the time our liquid's going to be of water, but it's generically true for liquids too. Okay. What if I asked you to dissolve a liquid in a liquid and you heated the liquid up? Would that have any effect at all? Depends. It depends. You know how you can smell alcohol? Because alcohol is a vapor pressure. It means it's volatile. It is easier to boil. So it's easier to turn into a vapor. It's easier to turn into a gas. So when alcohol is hot, it starts turning into a gas. When water is hot, you got hot water. You have to really, really try to make water boil. Try really hard. Water really likes to stick to itself. So if you've got two liquids and one of them is volatile, then heating it up is going to be counterproductive. It's going to be counterproductive. So heating it up, true. Don't know. It's going to have to be a case-by-case basis. What if you had a gas? Gases can dissolve in water. We don't think about that a lot, but gases do dissolve in water. Anybody ever seen a fish? These things called fish. They're amazing. Fish don't have to come to the surface to breathe. They have gills, which extracts the dissolved oxygen in the lake water or the seawater. And only like lake fish or river fish ever come to the surface and take a gulp, and they don't even need to. There are fish in the ocean that have never seen the surface. So oxygen, the gas, dissolves in the liquid quite easily. What if we heated this liquid up? What would happen to the dissolved oxygen?
Would it separate?
Yeah. Gases become less soluble in hot liquids. Solids become more soluble, gases become less. If you buy a bottle of carbonated beverage, like a Coca-Cola or a Pepsi-Cola, and you want to keep the fizz in your bottle, what do you do to the bottle? You keep it cold. Anybody that's ever left a bottle of carbonated beverage in the car on a warm day and has come back and opened that bottle, what happens? Oh, it goes nuts and then it goes flat because all the gas wants to escape. Gases respond to heat energy. Heat energy is kinetic energy. Kinetic energy is the energy associated with motion. Gases have a lot more inherent motion in them than liquids do, and solids have basically none at all. They just have a little vibrational energy. So any heat is going to be picked up by the gas first. Those gases start zooming around and then they want to leave solution. Lived in Michigan for 11 years, and it starts snowing in October and it doesn't stop snowing until April. And the lakes freeze over and you think, poor fish. Oh, poor fish, because they can't come to the surface. Fish don't care. There's already enough dissolved oxygen in the lake, and the cold weather actually dissolves more oxygen. The fish never need to come to the surface. The surface freezes over for a couple of months. Fish are fine. It's in the summer months that they struggle because the heat makes the oxygen leave the pond or the lake. Okay. What else could I do other than heating up the liquid that would increase the chances of me making a solid dissolve? Yeah. I'm going to call that agitation. If you stir or mix or shake, you increase the likelihood that liquid and solid interface, have a meaningful interface. What happens is, if you have a block of solid and you expect liquid to dissolve it, well, liquid can only dissolve this surface, this solid, at the surface. So the liquid touches the surface, chips off a little bit, and puts the solid into solution. Well, it never goes very far. It's a thing called diffusion. We'll talk about diffusion actually later on. We're going to put a number to it. The dissolved solid never really gets too far. And so this solid at the surface, when it looks out at what's right next to it, sees more solid, which is preventing it from dissolving. What it needs to see is more liquid. And we do that by mixing the whole thing up. So the solid can only be dissolved at the surface. It dissolves, and then you mix it, and you give more fresh liquid to the surface, and then it dissolves, and then you mix. So agitation increases solubility of the solids. there's a component of diffusion in the heat as well, because the heat gives the liquid kinetic energy, which allows it to move, sets up a thermal current, and diffusion plays an important role in this first one as well. We'll come back and talk about diffusion at the end of the chapter. Anything else I can do? Okay.
Kind of a stab in the dark, but I don't know. If you add, okay, this, never mind.
If, these are vaguely the same size. If I say this is a block of salt, sodium chloride, go dissolve it. So you get a beaker of water and you plonk the block of salt in the water and you just sit there and you watch it take 2 hours to dissolve. Or you could, yeah, I could take a hammer to this and smash it into smaller pieces and then put those pieces into solution. How would that help me?
The liquid will touch more of the surface.
Surface area. If you make the particle sizes smaller, you increase the surface area and you can only dissolve at the surface, right? So if I take that cube and I broke that cube in half, then I get all of that, and I got 2 pieces, I get all of that extra surface area. If I smash it up into little pieces, I get so much extra surface area. So smaller particles, which is larger surface area. Increases solubility. Anything else we should think of? What's left? We've got size, we've got heat, I've got stirring or agitation. Think of one other thing.
Chemicals?
If I took a lump of salt and put it in water and then pressurized the gas above the water, or just pressurized the water, what would that do? Yeah, I'm getting like, huh? Almost nothing. Almost nothing. Here's why. Solids are close packed. Their particles, their atoms are already really, really close to each other. Solids don't get compressed very easily. Liquids have a little bit of a gap, which allows them to have that fluid behavior, that they can move around each other. Gases have very large distances between the smallest particle, whether that's an atom or a molecule. So gases can be compressed, pressurized. Liquids can be pressurized a tiny bit, and solids basically not at all. So trying to have an effect of dissolving a solid in a liquid by changing the pressure, not going to matter. But dissolving a gas in a liquid will matter. Only for gases. If you want to make a gas dissolve in water, do you want that gas to be pressurized or not pressurized? How do you think they get the carbon dioxide into your carbonated beverages? Just wait until it happens, or do they squirt the gas in? Yeah. So increasing the pressure will increase the solubility of a gas in a liquid. Okay. So those are all physical behaviors. Let's look at a little bit at the chemical behavior of what's going on in a solution. And we've been spending the most recent time looking at ionics. So we'll look at some ionic compounds dissolving in water. We already hinted at this last week. Have another look. I might have to clean the board. So when ionic compounds dissolve in water, they dissociate. Let me go get something for the board. So all of our ionic materials, sodium chloride, potassium nitrate, whatever it was, we lead with the metal. Metal comes first. Metal makes a cation, gets oxidized, makes a cation. The non-metal components gets reduced, makes an anion. And then the positive and the negative stick together. So here's the thing. They only stick together when they're in the solid form. When you put them in solution, they split apart. Let's look at that process. And then go back and look at a reaction and do something very, very clever. Okay. Because last week, we looked at acids and bases always did the same reaction. And I said, oh, the other things don't matter. We'll prove that today. So when ionic compounds dissolve in water, they dissociate. So here is sodium chloride. It's a solid. I'm going to put that in the presence of water. You can actually write that as a reactant. Doesn't have to be. Sometimes we write it over the arrow, but that's more of a organic reference than a general chemistry reference. Here we go. These are our state symbols. And the state symbol is solid, liquid, gas, and AQ. AQ means aqueous solution. So, sodium chloride as a solid dissolves in liquid water and makes sodium chloride as an aqueous solution dissolved in water. Can't see it anymore. Well, sodium chloride in solution splits apart to make a cation and an anion, and they are solvated ions. The solvent, which in our case is water, aids them splitting apart. We talked about this a little bit last week because we knew that pure water does not conduct electricity, but salt water does. Okay, so how's that happening? Well, the separation of charge facilitates the conduction of electricity. We might have put a word to this. I'm not sure.
The electrolyte.
These are called electrolytes. Electrolytes, couldn't remember if I'd said it or not. Electrolytes are dissolved ions. Where have you heard the word electrolyte before Chemistry 1? Gatorade commercials. Yeah. Guess what happens if you run a long distance and intake no food, no water, no nothing? What happens to your body?
You feel exhausted.
And potentially worse.
Yeah.
Because you sweat. And when you sweat, what does sweat taste like? Yeah, you're sweating out liquid plus salt. Why does your body need salt?
It's a conductor.
Yeah, because the salt, we've proven with the little light bulb sketch last week, you can actually do it for real if you want to, conducts electricity. Your cells fire neurons and have electrical impulses, nerve impulses, and they are controlled by the ion balance in your body, in your serum. And if you sweat, but you take in no additional liquid, you lose salt, therefore you lose impulse. What if, while you were running, every time you went past a water station, you intook lots and lots of water? Is that a good thing or a bad thing? That's actually a bad thing, because you are replacing the water, yes, but you're not replacing the salt. And so you're diluting the salt that's left in your blood even further. Did you know that you can die if you just drink water? Lots and lots and lots and lots of water. It's called hyponatremia. It's not the water that kills you, it's the dilution of the salt in your bloodstream, and your brain swells. You have a thing called osmosis, which again we will talk about at the end of this chapter. And the key was, University of Florida figured out that if they put salt in the fruit punch, then the football players didn't get cramps. So you replace the salt in the sweat as well. These are electrolytes, okay? How's that going to work? This is a little bit of a stretch because we haven't seen this yet. We haven't learned the science underneath this yet. But water is an oxygen and two hydrogens. And it's L-shaped. And what happens is, if you put a sodium into solution, or in fact any metal ion, it points the oxygen end, the right-hand side of the periodic table, towards the sodium and just surrounds it. It envelops it in a little bubble. It's not a physical bubble, it's a conceptual bubble. And the chloride, which is the opposite, is negatively charged. Water, which again is L-shaped, points the atom from the right-hand side of the periodic table at the chloride and solvates it. So there's this thing, and we'll learn more about it later. We can't quite do it right now. It's called a solvation sphere. And you need about 11 waters to completely surround a sodium ion. And when things are positive, the oxygen points at them. And when things are negative, the hydrogen points at them. Because we're going to learn later that oxygen retains an ever so slightly small negative charge, and hydrogen retains an ever so small positive charge. Okay. All right. Remember this from a week ago? Acid plus base makes water plus salt. Here's my acid, that's hydrochloric acid. There's the base, that's called sodium hydroxide, and it makes water. And in this case, the salt is sodium chloride. What I've got up on the board is called a balanced equation. I'm going to do two things to this equation. At the end of those two things, I will have discovered a very, very simple answer. A simple answer that is true in every single case. In order to get there, I have to make it look ugly, okay? You have to break eggs if you want to make an omelet. So, the first thing I'm going to do is write something called a complete or total ionic equation. And in a complete ionic equation, you take everything that's written on the page and you turn it into its ions. Because in solution, HCl, left-hand side of the periodic table, right-hand side of the periodic table, this is ionic. Left-hand side of the periodic table, right-hand side of the periodic table, this is ionic. That's a liquid. We're going to skip that one. Left-hand side, right-hand side. These are all ionic, and ionic things split apart in solution. Okay. That seems like a lot. I've taken everything ionic in my first balanced equation and allowed it to dissociate into its component ions. So the HCl becomes an H plus and a Cl minus, and the NOH becomes an Na plus and an OH minus, and the NaCl becomes an Na plus and a Cl minus. Okay. These are called equations. Called equations. The arrow is an equal sign. Whatever's on the left has to equal what was on the right. We didn't do very many examples of that. We just said it was and assumed that we would be okay with it. But the mass on the left has to equal the mass on the right. The number of atoms or ions on the left has to equal the number of atoms or ions on the right. And in a mathematical equation, if you have a term that is on the left and the right of the equal sign, what do you do with those terms? They cancel each other out. Because if I move a positive value across the equal sign, it becomes negative and it will cancel the other one out. Okay, so let's look. H plus. Does H plus appear anywhere else on that line? So let's leave it. Cl minus. There's one right at the end. They cancel, they're gone. Na plus. Yeah, there's one at the end. They're gone. OH minus. No, only got one of them. And H2O. Only got one of them. Okay. That leaves us with something called the net ionic equation. And the net ionic equation for hydrochloric acid and sodium hydroxide turns out to be that hydronium plus hydroxide makes water. And it didn't matter whether this came from HCl or HBr or HNO3 or H2SO4 or H2SO3 or H3PO4. This reaction tells us that the chloride was just a delivery agent for the H+, and that the sodium doesn't matter. Doesn't matter. This could have been a potassium, could have been a calcium, could have been something else. Doesn't matter. It's not part of the reaction. So these things that got cancelled, these are called spectator ions. Spectator ions appear in the balanced equation, but do not play a role in the underlying reaction. They remain dissociated all the way through. Okay. Which is why we said last week that the name of the acid and the name of the base didn't matter, but they are coming together to make water, and making water was the whole point. Okay. Questions about that? Okay. Still writing? Who's still writing? A couple of people. I'll only erase the top part. Okay. Well, wouldn't it be great if everything that we handled was just the same and everything dissolved with the same amount of ability? That would be a little bit boring. It isn't what happens. Individual compounds have their own unique solubilities, but there are some rules. There are rules of solubility. Let's see which is the best pen. And it all comes down to how good of an electrolyte are you? So if you are an electrolyte, you are a dissolved ion, right? An electrolyte is a dissolved ion. We're going to put you into two categories. You either are a strong electrolyte, which means you dissociate really easily, or you're not, in which case you're going to be a weak electrolyte. Anything that contains a strong electrolyte is guaranteed to dissolve in water. And there are rules, and they're fairly simple. All sodium salts dissolve in water. All of them. Every last one. Sodium chloride does, sodium bromide does, sodium iodide does, sodium nitrate does, sodium sulfide does, sodium phosphide does, sodium chloride does. Anything that you can think of that starts with a sodium, guaranteed to dissolve in water. All potassium salts dissolve in water. Rubidium and cesium salts do as well, but we're not going to see any of those. So let's just keep it to the things that we're going to see. All the salts from group 1, the sodiums and the potassium salts, every last one of them dissolves in water. That was easy. All ammonium salts dissolve in water. How do I recognize an ammonium when I see it? What's an ammonium ion look like? NH4 plus. Good. Ammonia, the gas, is NH3. Okay, these are our cations. If the cation part of your ionic compound is a sodium, a potassium, or an ammonium, it dissolves in water. Okay? All nitrate salts are soluble in water. All of them. How do I recognize a nitrate when I see it? That's an NO3 with a 1 minus on the top. Every last nitrate is soluble in water. Okay. So most of the periodic table are metals, right? We've come to that conclusion already. Some of those metals are reluctant to dissolve. There are a bunch of metals that we say they precipitate, they fall out of solution, they make insoluble salts. But if I take anything at all on that periodic table and I dissolve it in nitric acid, it's guaranteed to dissolve. Guaranteed to dissolve. There's a rumor, it's not a rumor, it's a true story, that Niels Bohr was a Danish physicist. He won the Nobel Prize for physics somewhere around 1930. Right about the time when Germany annexed Denmark. And rather than let the Germans get their hands on his Nobel Prize, which are made out of gold. They're actually made out of gold. He dissolved it in a bottle of nitric acid. He dissolved his gold Nobel Prize medal in nitric acid, and it sat on a shelf during the entire Second World War. And at the end of the war, they precipitated the gold and restamped the medal for him. So anything that is a nitrate, guaranteed to be soluble. That's where the rules end. Everything after this is kind of sort of, maybe. Most chlorides are soluble, except, now it turns out there are a handful of heavy metals on the periodic table that are reluctant to dissolve, and it's the same for all of the maybes on this list. Mercury, Hg, doesn't like to dissolve. Lead doesn't like to dissolve. What else is up there?
Silver?
Silver's actually, silver chloride absolutely won't. There you go. Thank you. And cadmium. These, not particularly happy as chlorides. Most sulfates are soluble, except mercury, lead. I think silver sulfate's not so bad. Cadmium and barium. That one's a little bit odd because that one comes from group 2, where most things are soluble. And then we have one that goes the opposite way. Let me just check what the time is. Okay. Most hydroxides, and this one's a little bit strange, because this is the acid plus base thing. Hydroxide is the base, and we would assume, I think I would have assumed that these would all be soluble to get the most amount of water available out of your reaction. But it turns out that's not the case. Most hydroxides are insoluble, except, yeah, anything that's on this list. Anything that's on this list gets to be the exception here. So, except your lithiums, your sodiums, your potassiums, and your ammoniums. Which is why when the book tells you calcium hydroxide and hydrochloric acid get together and they do an acid-base neutralization, they're telling the truth, but calcium hydroxide really doesn't want to be soluble in the first place. You can only squeeze a little tiny amount of it in. Okay, Wednesday, we've managed to avoid doing it the entire day. Wednesday, we're going to turn mass into moles and then dissolve those moles into a known volume of liquid. This is called concentration. It isn't difficult, and yet it's something that year after year after year people struggle with. If you were to read ahead or watch ahead to the section on concentration and dilutions, you would be doing yourself a favor. Okay? I'll see you Wednesday.